Having looked at another definition of trig functions within the context of a right triangle, we want to revisit identities and see if they still hold. It turns out like we can go and do proofs to our heart's desire, or we can just not and know that all the trigonometric identities still hold. So, all the properties like period property, even and odd, and the Pythagorean identities, reciprocal identities, etc., all those still hold. So just a quick example of this is using the side lengths of the right triangle. So, okay, let's get a right triangle drawn just for reference. Okay, so let's see, this we'll call theta, and then with respect to theta, this is going to be the opposite side, adjacent, and hypotenuse. It says prove the identity is that, prove, what is Professor Bright doing? Well, we're going to have fun. That's always my answer. So with a proof, generally what you want to do is you want to start with one side and work towards the other. So let's start with tangent squared of theta plus 1. Okay, well, and then see if we can simplify it down to secant squared. Okay, all right, so tangent, let's look at tangent in this triangle. Well, tangent we know is opposite, right? It's opposite over adjacent. So let's see, it's going to be opposite over adjacent, all squared plus 1. Okay, and I'm just going to, carry the arithmetic through opposite squared over adjacent squared plus 1. And this 1, if I want to add these, right, I need a common denominator. So I'm going to make that adjacent squared over adjacent squared. Okay, and well, okay, this is going to be opposite squared plus adjacent squared over adjacent squared. And remember, we still have the Pythagorean theorem. Hypotenuse squared is equal to opposite squared plus adjacent squared. Okay, so I'm going to use that little fact right in there to simplify this thing all to hypotenuse squared over adjacent squared. Okay, and I think if you look at that, that actually ends up being, if we do adjacent or hypotenuse over adjacent, that is indeed secant squared of theta, right? Because cosine was adjacent over hypotenuse, so secant is the reciprocal. So there we go. We did a proof. Yay, proofs. And then you're like, please never do that again. All right, so wanted to mention that about identities. Now the next bit is new. We're going to talk about another property called cofunctions. You notice that a lot of the or I guess 3 of the 6 functions, trigonometric functions that we've been working with, have a prefix of co attached to them. What does that mean? So there is this idea of cofunctions. The idea is that they, well, let's just kind of go through a process here, okay? So angles in a triangle must sum to 180. Yep, got that. In a right triangle, one has to be 90. Okay, the others have to add to 90, meaning that they are complementary. Notice there's a co in complementary, okay? So let's look at this in more detail. All right, let's label our sides on our triangle. Okay, I'm going to give C, lowercase c, the name for the hypotenuse. And then the other 2 legs I'm going to label as A and B. We're going to call that a right angle. Okay, and we have theta 1 and theta 2. Okay, so mathematically we represent complementary, right? That idea, we would say that theta 1 plus theta 2 is equal to 90 degrees, right? I could rearrange this, solve for theta 2, say, and if I solve for theta 2, I'd have theta 2 isolated is equal to 90 degrees minus theta 1. Okay? And so that's fun, but okay, we're just kind of going forward here. We haven't got to why cofunctions are so important, but let's think about taking a trig function and its cofunction and evaluating them at complementary angles. So let's look at sine of theta 1, and then its sine's cofunction would be cosine. So let's see, we have cosine, and then we're going to use the complementary angle, so theta 2. Okay, so sine of theta 1 is going to equal, okay, so from theta 1, right, I have to do opposite over hypotenuse. So this is b over c. And then cosine of theta 2 would be adjacent over hypotenuse, also b over c. Oh, they're the same. That's something very nice. So cofunctions evaluated at complementary angles are the same. You could do this also, you could reverse these. So if you do sine of theta 2, that is going to equal a over c, which is the same as cosine of theta 1. Okay, that's neat. In all, okay, generally, if we have sine of theta 1, okay, I should make this comment. If theta 1 plus theta 2 is a sum to 90 degrees, then sine of theta 1 is equal to cosine of theta 2. And similarly, if we substitute in what we saw for theta 2, this would be 90 degrees minus theta 1. All ways to express the same idea, same value, okay? And that's what the formal definition of a cofunction says, okay? You have an acute angle theta, and then we have f of theta, and then this, remember this would be the complementary angle, okay? Same thing here, just talking about complements. So in finding one trig function, if we want to find another cofunction or another function of the same value, find its cofunction evaluated at the complementary angle. That's the big takeaway. I'll repeat that. If you're being asked to find another trig function of the same value, evaluate the cofunction at the complementary angle. Okay? So you can see all the different cofunctions, blah, blah, blah. I'll let you read it. Okay, so in action here, I have cosine of 75 is equal to this. Okay, it says find a cofunction with the same value. Oh, that's literally what I just repeated very slowly again. So I don't much care about this value. Okay, I could really care less. If I want to find a cofunction with the same value, whatever that value might be, okay, I know the cofunction to cosine is sine, and then the complementary angle, right, I would find by doing 90 minus whatever the angle that I have is, 75. So sine of 15 degrees after I simplify. Okay. Now, in reality, how do I make sure that my answer is correct? Well, I would, take a calculator, substitute this in. I might get a decimal form of this if I'm using a calculator. And I would take a calculator and substitute that in, see if I get the same thing. If I do, great. Then we're good. And I check this on a calculator and it does work out. Okay. So next one, tangent of that. Okay, so tangent, again, I don't really care about the value, but I do care about the cofunction to tangent, which would be cotangent. So cotangent, and then now this one is in radians, so I could convert this to degrees. I'm not going to. I'm just going to say 90 degrees. Remember, in radians is pi over 2, so I'm going to work with pi over 2 minus pi over 5. Okay, and we might need to get, common denominators, so you get, 5 pi over 10 minus, 2 pi over 10. So then in all, this is the same as cotangent of 3 pi over 10. Okay, so cotangent 3 pi over 10 would be equivalent in value to tangent of pi over 5. All right, so cofunctions, algebraically, they're going to have the same value as the other cofunction evaluated at the complementary angle. That's a big takeaway. Later on, we'll see some interesting properties when we're looking at their graphs, but that's for a future class.